estimate, let me erase it, and try to translate in mathematical terms the fact that I refer to intervals. And let me define, for instance, the frequency of a variable. Let's suppose that I want to estimate the frequency of a variable x. And let me refer to an interval. So let me get the frequency that x minus delta x is less or equal than capital X, less or equal than x plus delta x. So what is this? Capital X is the random variable, which can be extracted by chance, and lowercase x is a given value for the random variable. So when I write this relationship, it means that I am interested in the frequency that a random outcome from capital X is included in this interval, lowercase x minus delta x, lowercase x plus delta x. Which means that if I refer to the real axis, the real axis of capital X, I have x here, and this is x minus delta x, and this is x plus delta x. So I look at an historical time series of capital X, and I count the number of times that values fall within this interval. Let me see, to use the same symbol, okay. Here it's written in a slightly different way, but let me compute this in this way. So n is the total number of values that I'm looking at, and capital N of x is the number of times that I get the random variable within that interval. Okay, this is quite intuitive, but now we need to pass to probability, because this is frequency. And in order to go to probability, of course, you already know that we need to increase the number of experiments, capital N, and make it very large. So let me define now a function fx which I call probability density. And before defining it, let me make a concept clear. Here I'm looking at an interval, but what I'm interested in is to get a probability that refers to a given value of the random variable, lowercase x. I need to refer to an interval because, for the reasons that I explained before, because I'm dealing with real numbers. But still, I am interested in describing the probability for varying values of the random variable, in this case varying lowercase x. And therefore, in order to refer to a specific value, I need to make this interval very small. Because if I enlarge the interval too much, it becomes not representative of what I want to study. And therefore, while I increase the number of experiments, I also have to decrease the width of the interval. And therefore, let me define this probability density as the limit as delta x tends to 0 of the frequency f x minus delta x less or equal than capital X, less or equal than x plus delta x. Basically here I wrote it in a slightly different way because I put a semicolon in order instead of this extended symbol. So in what is written there is a semicolon that is meaning this inequality. Also, there is one thing that I'm noticing now, which I forgot, and I will make a correction here. The limit should be for delta x that tends to 0, but also n tending to infinity. And it's not written there. I will make the change. Of course, because if you restrict the interval, which is motivated by the fact that you want to refer to a specific lowercase x, as you restrict the interval, you need to increase the number of experiments. Otherwise, you may get, in a short interval, you have a lower likelihood of getting an outcome that is falling into the interval. So you need to increase the number of experiments. So this is the probability density function or probability density distribution. So keep in mind that this fundamental step. When we turn from integer variables to real variables, we need to refer to the density of probability, which takes the place of individual probabilities of each event for the integer case. So instead of probability of each event, you have probability density, because the number of events tends to infinity, becomes infinity, and therefore you need to refer to probability density. So, let's see an example of the Gaussian distribution. Let me see if I have a, yeah, here I have an example. This is an example of a probability density. You have x here, you see capital X, and here you have the probability. Here the symbology is a bit different because this figure is taken by Wikipedia. But here you have the probability of a lowercase of each individual lowercase x. And you see that you have these different shapes for the probability density. This is an analytical function which is called the Gaussian or normal distribution, which I think you already studied in other subjects, which basically describes the probability density for several different outcomes. This is just an example. And this is already the result of interpolating probabilities of individual events. So this is an analytical function. So it's already the result of an interpolation. Now, let me refer to the real ax of x. And let's assume that we have estimated the probabilities for each individual value. Therefore, getting something like, let's suppose that we start from 0, and let's suppose, let's put 0 here. And let's suppose that we have a function like one of these that expresses the probability density. So in this case, it looks like we have a higher probability around 0, and the probability that decreases along the negative values and the positive values. Now, what happens if, after having estimated probabilities in this way, you make the sum of all the probability densities, and let's suppose that you give to delta x a given value, and after assigning to delta x a given value, let's suppose that you compute the sum of all the densities. Basically, you see up there that the frequency is given by the number of times that your value falls within an interval divided by the total number of experiments. So basically, if you take your, I draw again the ax here, let's suppose that you divide it in 4 intervals, and therefore let's suppose that you start from 0, 1, 2, 3, 4, and this is your first interval. So basically, here you have 0.5, here you have 1.5, 2.5, 3.5, and you center your first interval around here. This is delta x1, and then you have here delta x2, delta x3, and here you have delta x4. Let's suppose that your n is equal to something like 60, and let's count the number of times that each of these 60 numbers falls within these intervals. And you may get something like, let me call it n 0.5 equal to, let me use the same symbol, nx, yeah, equal to 8, and 1.5 is equal to, let's say, 15, and n 2.5 may be equal to 25, and n 3.5 is equal to 48/12. And then you can compute the probability density in this way. So let's say that f of 0.5 is equal to 8 divided by 60 divided by delta x, which is 1. And you get a number. Which is, in this case, is 4 over 2 over 15. Let me see, 4 over 30, yeah, 2 over 15. And then you can compute the other numbers. Okay, so what happens now if you, let me delete here. If you compute the sum of the fx times delta x, this is equal to 1. Basically, this says, and this is clear in this case because the delta x is equal to 1, so basically you have the summation of 8 divided by 60 plus 15 divided by 60 plus 25, etc. is equal to 60 divided by 60, and therefore it's 1. But even if your delta x would be 2, for instance, you get the same result because you divide by 2 and then you compute, again you multiply by 2, which means that the sum of the probability densities is equal to 1. And this, in general, brings me to say that the integral between the integral of fx in dx is equal to 1, provided the integral is extended over the whole domain of the random variable, and I put a d here, which means the whole domain. The integral of the probability densities is always equal to 1. Like the sum of probabilities of discrete events is equal to 1. This is a non-resulting probability. Whatever analytical function you use to describe the probability density of a random variable, the integral should be equal to 1. Now, what if I don't compute the integral on the whole domain, but on only a part of it? So here the whole domain is this axis here. So this is my domain D. And if I compute the densities, the summation of the densities over the whole domain, the summation is 1. I already proved it here. What happens if I extend my summation, my integral, from the lower limit of the domain to half domain, for instance, not the whole domain? Of course, the integral is, or the summation is lower than 1. Okay, and what does it mean, this integral summation? So keep in mind that I say integral summation because the integral is nothing else than a summation extended over infinitesimal intervals. And therefore, but the integral is nothing else than a summation at the end of the story. From an engineeristic point of view, from the point of view of an engineer, the integral is nothing else than a summation. We use the integral when the intervals over which we sum are very, very, very small, and therefore they become an infinite number of intervals. But speaking of an integral, speaking of a summation, is the same thing. And keep it in mind, this is a basic recipe to make calculus easier. So keep in mind that the integral is a sum. and the derivative is a difference. This is extremely important. So what happens if I extend my integral, which is nothing else than a summation, up to half domain, like up to here? So what is the integral in this case between 0 and 2 of fx in dx? First, we call it capital F of 2, or capital F of whatever x value. Some textbooks call it lowercase p. And keep in mind that the terminology here, it's depending on the textbook, may be varying, not only the symbols, but also the terminology. So what is this integral? First, we call it cumulative distribution function, or cumulative probability function. Let me see how I call it here. Cumulative probability. So this is the cumulative probability. Cumulative, of course, because it's summation, and therefore you can understand that people wanted to call it cumulative. It's a summation, as I said, and this gives us the probability that x values are lower than 2. Because between 0 and 2, if I integrate, if I take the summation of probabilities that x is between 0 and 2, I obtain the probability that x is lower than 2. So if I integrate the probability density over a finite interval, I get the cumulative probability that the random variable is within that interval. And in this case, it means that I obtain the probability that x is lower than 2. And it's also called probability of not exceedance, which is for us extremely important in hydrology, water resources management. Probability of not exceedance, which means probability that I don't get a flood, basically. So when I integrate the probability density between the lower value of the random variable, in our case is always 0, because when we refer to river flows, the lower value is always 0. So when I integrate the probability density between 0 and whatever value, I obtain the probability of not exceedance of that whatever value. What I'm saying, I understand that it's difficult to follow, but if you go back to the definitions that I provided, which are only based on counting outcomes, you can easily understand that I'm just counting the number of times that my random variable is below, in this case, 2. Questions? Because so far what I defined is probability for integer random variables, probability of discrete events. And then I turned to probability for real values. So I defined the probability density, and I said that if I integrate the probability density, I go back to estimating the probability that the random variable falls within a certain interval. And again, it's not easy to follow, and the difficult thing is this this need that we have to deal with real variables instead of integer ones. And this brings me to the need of defining the probability density and to explain that if I integrate the probability density, I obtain probability of not exceedance, probability of the variable falling within an interval, which is what I'm interested in. And when I deal with droughts, it's the same thing. I need to know when the water level is below a certain number. I need to know when the water flow is below a certain number. And therefore, what I do is to estimate the probability density of individual values and integrate between 0 and a certain number. So let me make a final drawing. Let's suppose that I am on a river flow and I have flows, and let me now indicate them with Q, which is easier, ranging from 0 to 100. Whatever the unit is, and let me write here the probability density fx for this time series. And what I have to do is splitting in intervals. And for each of them, compute my histogram. And typically I obtain something like that. And the way in which I estimate it is fx is equal to n. X is lower, x minus delta x lower than x, lower than x plus delta x, divided by n times delta x. And then let's suppose that here we have 30. And I'm interested in knowing what is the probability that the river flow is lower than 30 because I want to estimate droughts. Okay, therefore, I compute the probability capital F that x is lower than 30 as the integral between 0 and 30 of fx dx. X computed in this way, and in this case it becomes a summation of 3 numbers. That's it. Now, we still have, I still have the wish to get an analytical function describing these probabilities. And I want an analytical function because this allows me to interpolate and extrapolate. You may say, why do you need an analytical function? Because you can substitute integral with summations and this would be fine. Yes, it's true. But I want to be able to extrapolate, for instance, because my data may be varying from 0 and 100, but I might be interested in knowing the probability of river flow equal to 200, and therefore I need to extrapolate. And to extrapolate, I prefer to use an analytical function. And so this is why the literature provided several analytical functions for the probability density. And people tried to look for functions that can easily be integrated. Why is that? Because you see that I need to compute integrals in order of probability densities in order to obtain results that are technically meaningful. I mean, it's not technically meaningful if I look at the probability density. It's technically meaningful if I integrate it. And therefore, people tried to look for functions that can be integrated, analytical functions that can be integrated. But then, you know, it was not easy. So in some cases, they gave up and proposed a function that worked well, but needed to be integrated numerically. And this is the reason why people looked for parametric functions, is that you want a flexible analytical function in order to be adapted to several different rivers, several different real-world situations. And so, a classic example is the Gaussian distribution, which is this one. The Gaussian distribution is very well known. It's called also the normal distribution. And you see that it has a striking feature. It's symmetric. So if you look at the shape of the analytical function, it's symmetric around the central value, which is not very good in hydrology because river flows and rainfall typically are not symmetric. If you look at the probabilities of river flows, you have already a series for the Po River, and you would be able to estimate the probability density for the Po River in R very easily. Maybe tomorrow we have time to do that. And you will see that it's not symmetric what you get. Indeed, this would be very helpful. Tomorrow I will propose you this preliminary exercise. But if you are able to take the time series of the Po River and to derive this graph, it means that you perfectly understood what probability density and probability in general is. Okay, and this is a particular shape which is very well known, and it has a striking feature. The striking feature is, besides being symmetric, is that any random variable that you may consider has its own probability distribution. So river flows, rainfall, temperature. You can consider these meteorological and hydrological variables as random variables, and you can estimate probability distributions. And of course, you get very different shapes. You expect a different shape if you look at temperature, variability of temperature, frequency of occurrence of temperature. Instead of looking at river flows, you expect a different shape for this graph of probability. But now, let's suppose that you integrate over time. So the river flows are not observed at daily time scale, but you refer to the monthly time scale. And then let's refer to the annual time scale and maybe integrate again over 10 years. So it can be proved with a proof that we don't make that as you integrate any type of random variable over increasing intervals, increasing time intervals, you end up with asymptotically to a Gaussian distribution. And this is a striking feature of chance. And you can perfectly see that whatever randomness is, there is a regularity in it. In the past, some people thought that this was a proof of the existence of God. Indeed, it's a proof of existence of regularity in chance. So whatever random variable you consider, you average a random variable that you can express as a function of time, you average it, you average over increasing time intervals, and you get the Gaussian distribution. But for short time scales, like the ones we are interested in, river flows and rainfall, they are not Gaussian. In order to get Gaussian river flows, usually we need to know at least the annual scale. Okay. Now, I think that we need to quickly turn from the theoretical treatment to our technical problem. Our technical problem is to estimate extreme flows. Sustainability means look at the extremes and check if they are sustainable. This is a meaning of sustainability. Of course, you don't look as business as usual if you want to check sustainability. Business as usual is usually sustainable. You need to look at extreme situations. And therefore, we need to look at the extreme values. They can be extremely low or extremely high. So, the technical question is, how can I estimate extreme values? If I look at a river, what can be the very minimum flow that the river may deliver? What can be the very maximum flow that the river can deliver? So, this is our question, and we focus on the high flows, but what I'm saying can be very easily extended with very small changes, very irrelevant changes to the case of low flows, but let's refer to the high flows. And we need to define our experiment. Probability, keep in mind, refers to events. Events that we can associate to an experiment. Am I interested in flood flows? My experiment is the flood, of course. So I need to look at floods. And if I want to look at high flows in general, because I am interested not only in floods really, I'm interested in high flow events, not only the ones that caused the overtopping of the river. I'm interested in extreme events. Some of them may cause flooding, some of them may not. Also, you know, floods sometimes is due to the collapse of a levee. So it's more appropriate to say that I'm interested in studying high flows, and therefore I need to define what high flows are. I need to define an experiment. So let's suppose that I have a time series.